This is the full section of the algorithms on graphs chapter, and this is using Dijkstra's algorithm to find the shortest path. So as the name suggests, this is going to be an algorithm that allows us to find the shortest path through a network. Okay, now just like any algorithm, there's going to be a series of steps to follow, and there also is going to be some sort of working or some sort of way of listing what we're doing. And the way that it works with Dijkstra's algorithm is that every vertex we're going to do a box like this, and we're going to use this box to sort of keep track of the working that we're carrying out as we carry out this algorithm. Now in the exam you'll have a network and you will have boxes drawn like this. There may be some values in here, or it may be completely blank, so you'll need to know what to put in each box. The very first box here, we put the vertex label here, so whether that's like A, B, C, D, S, T, whatever letter is at the vertex, we put that in this box here. In the second box here, we put the order of labeling. As we go through this algorithm, we're going to be labeling our vertices in a particular order. And this box here is just going to contain the order in which we've done it. So is it the first, the second, the third? So this will just contain a number like 1, 2, 3, 4, 5, something like that. This box here at the end will contain a number which we call the final label. As we do the algorithm, you'll see that this final label is basically the shortest distance to this to get to this vertex. And the box at the bottom here is going to contain maybe a series of numbers, maybe 1, 2, 3 different numbers in here, and these are what we call the working values. And as we go through the algorithm, you'll see that these values are basically the different distances or the total weights to get to this particular vertex, because there may be different ways of getting to this vertex, where and then once we've found like the lowest weight, the shortest distance to get to this vertex, that then becomes the final label. So let's go through the algorithm. So the first step in the algorithm is to label the start vertex with the order of labeling number 1, because it's going to be the first box that we label, and the final label 0. This basically means the distance to the start vertex is 0. So there won't be anything in the bottom part of this box because we've got no working values, and we'll have a letter in here, and that will be whatever the start vertex is. So sometimes that's labeled as S or A, but there'll be a letter in there whatever the start vertex is. So this box will be by the start vertex, put the label of the start vertex there, 1 here and 0 here. Now the next step is to look at the vertices directly connected to the last vertex. Now at the start, that will be all the vertices connected directly to the start vertex, but as we go through the algorithm, repeat it, it won't be the start vertex, it'll be a different vertex, and add the weight of those vertices. So if you've got some vertices sticking out here, add those weights to 0, and then in those vertex boxes, write those values down as the working values. So for example, if I had, I don't know, 3 vertices here with different weights, 7, 3, 5, then what I would write down in these boxes here is I would have a working value of 7 there, a working value of 3 here, then a working value of 5 here. Okay, the next step would be to select the vertex with the smallest working value. So my example here, it would be this one here. Make this the final label. So I would actually put 3 here, make it the final label, and add the ordering of labeling. So this was the first order of labeling. So then I would label this as 2. Now, the next step would be to select the vertex with the smallest working value, which we've just talked about. But yeah, the next step would be to actually go back and repeat this step here. So this box that we've repeated here, for example, there'll be some vertices maybe coming out of this, and we carry out this same step again. The vertex that's, or the edges that are directly connected to this, and those vertices here, so I'll have some different vertices here, and we'll carry out this step again, add the weight of these vertices and write down this working value. Now what we'll find is as we go through this algorithm, these boxes here may have several working values in. So just a note here, in that we always use the smallest working value, the smallest working value. So if there's several working values in a box here, we just use the smallest one, and then we just repeat these steps until the end vertex has a final label. So when the vertex at the end, its box has a final label here, that's when we stop. And then what we'll need to do is to find the shortest route. Now to find the shortest route, we're going to have to work backwards through our network, looking at the values, subtracting the weights, and then picking the box where that subtraction gives the correct answer. Now, just looking at this on its own, it can seem quite confusing and complicated. So the best way is to go through some examples. So we're going to use Dijkstra's algorithm to find the shortest route from S to T on this network. So this is where we start, and this is where we finish. So typically in an exam, you'll have a diagram like this already given. Maybe some of these values will be filled in, but we need to make sure that we fill it in correctly to get full marks. So remember, the first thing we need to do is the start vertex we label as the first one. So that's the first one that we visited, and the distance to S is 0. So now what we're going to do is we look at the vertices that can be reached directly from S. Okay, so we're going to be looking at what we need to write in these 3 boxes. So we write down temporary working values. So I know this is weight 0, so if I add 5, this will be 5 to get here, 6 to get here, and 2 to get here. Okay, so the next step in the algorithm is to pick the vertex that has the lowest working value, which is this one here. We make its working value permanent, or its final value, and so this becomes the second one that we have labeled. Right, next step in the algorithm, this is when we go back and repeat. We look at the vertices that can be reached directly from the vertex where we've just put a final label in. So if we do that, so we've got a weight of 2 to get here, another 2 there, means that we're going to have the number 4 here, and here we've got 2, that's a weight of 12, so we're going to have 14 here. Now where we've got more than one number, more than one working value here, we always pick the lowest. So we could, if we wanted to, we could cross out the 6 so we don't get confused. Then the next step is to pick the vertex with the lowest working value, and that is B. So B becomes our next vertex. So we make the working value the final value, and this is the third vertex that we've labeled. Then we look at all the vertices that can be reached directly from B. Right, so those vertices are D and T. So we've got a permanent weight of 4. We add 4 to that. So that's going to give us 8 as a working value. And then here, 4 plus 8, this gives us a working value of 12. Next step, from those that have now got working values, the 5, the 8, the 14 and the 12, we pick the one with the lowest or smallest working value, and that's now going to be vertex A. So on vertex A, we make the 5 the final value or permanent value, and this is now the 4th vertex that we've labeled. So now we look at which vertices we can reach directly from A. Now that's only going to be D. So we have a permanent value of 5, add 4, so that gives us 9. Like this, we'll keep the 9 in. Now we won't cross out these lowest values just yet, maybe we'll leave that at the end. You don't necessarily have to cross them out, just realize that you're going to be using the lowest value. Right, so I've done that. That's the vertex that can be reached directly from A. I have 2 vertices now with working values. The one that has the lowest working value is D with 8. So 8 becomes my permanent value, and this is now the 5th vertex that I've labeled. I'll now look at the vertices that I can reach directly from D, and that's only T. So a permanent value of 8 plus a weight of 3 gives me 11. So now I can see that this is the only box that has working values now, and the lowest working value is 11, and it's the 6th and final vertex. So now that the finish or the end has a final value, the algorithm is now finished. I could leave these working values in here, or I could sort of cross them out. And then what I need to do is to work out the shortest route. I know that the shortest route has a weight of 11. I now need to work out how did I get here. So what we do, we take this final value, this weight of 11, and then when we work backwards, rather than adding these weights, we take them away. So here this would be like 11 minus 3, this would be 11 minus 8, and this one would be 11 minus 12. Now 11 minus 3 is 8, 11 minus 8 is 3, 11 minus 12, that's negative 1. So what I'm looking for is the previous vertex, does it have this number? So if I do 11 minus 3, do I get 8? Yes. So this is correct. Are there any other correct ones? Well, not this one, because 11 minus 8 is 3, and there's no negative ones. So this is the root here. So we'll just highlight that there, and we do the same thing here. We take this weight and we subtract these weights here and see which one is correct. So 8 minus 4 is 4, 8 minus 4 here is 4. So you can see 8 minus 4 is not 5, so it's not that way. 8 minus 4 is 4. So that means that this is the next part of our route. And then actually from here, there's only one place to go. Oh, actually, no, there are 2 places to go, because 4 minus 6 is minus 2, so it can't be that one. Make sure you write that down. So 4 minus 6 minus 2, so it's not that one. Here would be 4 minus 2, which is 2. Okay, so that tells us that we're now here. And then 2 minus 0, oh sorry, 2 minus 2, so this 2 minus that weight of 2 is 0. Okay, so that calculation is right, that takes us back to there. So that means that this then is the route back. So our route through the network starts at S, then we go to C, then B, then D, then T to get to the end. You could just write S, C, B, D, T like this, and it has a weight of 11. So if we're going to write a full answer, we could say the shortest route from S to T is SCB DT, and it has weight of 11. Okay, so we're going to use Dijkstra's algorithm again in this network to find the length of the shortest route. Right, so remember, first thing we do, this is my first label and it has a weight of 0. Then we want to look at the roots or vertices I can reach directly from A. So that's going to be these 3. So I can work out what their working values are. So this will be 8, this will be 18, and this will be 8. Then I pick the vertex with the lowest working value. Now I've got 2 choices because there are 2 vertices with the lowest working value. So I can pick either one. I'm going to start by picking B. Okay, so I'll make B the 8 the permanent value, and this is the second one that I've labelled. So now I want to look at what vertices can I get to directly from B, and it's going to be those 2. So I'll have 8 plus 15, which is 23 here, and then I'll have 8 plus 7, so I'll have 15 as my working value here. I now pick the vertex with the lowest working value, and that is C. So this will now be the third one that I've labelled, and its permanent value will be 8, or final value will be 8. And I'm going to look at the vertices I can get to directly from C. So this will be 8 plus 8, that's 16. Now I don't need to write it down because it's not the smallest, but I'll just, for completeness, I'll just put that in. And then what I will have here is 8 plus 12, so I'm going to have 20 here. Okay, so next step is now look for my smallest working value, and that is 15. So I will put 15 here, and this will be the 4th box that I label, or 4th vertex. I now look at the vertices that I can reach directly from D. Now that will mean that I've got 15 plus 6, so this one will be 21 here, 21 to get to there, 15 plus 9, so I will have 24 here as a working value, and then here 15 plus 6, that'll be 21. Again, I don't need to write it down because it's not a smaller one, but for completeness I'll do it. Then I look for the smallest working value. Now like before, I've got 2 choices. Oh no, actually just one choice, I forgot there's a 20 there. So 20 is my smallest working value. This will now be the 5th vertex that I label, and I look at the vertices that I can reach directly from F. Now that's just going to be the final vertex, so this would be 29 here. Now I look at the smallest working value, and that's going to be 21 here. So this will be the 6th vertex that has a final value of 21. Where can I reach directly from E? Well, it's only going to be the final vertex. So 21 plus 8, that's also going to be 29. Then I look at my smallest working value, which is the 24 here. So 24 becomes permanent. This is the 7th vertex that I've labelled. And then where can I reach directly from G? Well, that's just going to be H. So that would be 24 plus H, which is going to be 32. So I'm like 32 down. As I said, I don't need to. Then I pick the smallest working value, which is now in the final box, which is 29. And this will be the 8th vertex that I label. So now I need to work backwards to find out the root or root. Sometimes there's more than one answer. So starting with 29. So 29 minus 8 is 21. Yeah, so this root is fine. 29 minus 8 is not 24, so I'll stick across there. So I'll just put 29 minus 24. That's going to be 5, so it's not that root. Down here, 29 minus 9 is 20, so it could be this root as well. So 29 minus 20 equals 9, so we can go along that route as well. Right, so I'm going to colour code these roots because I've got 2 different ones. So let's go along the green route here. So here I would have 21 minus 6, which is 15. Yeah, so I can go along that route. 21 minus 8, 21 minus 15, getting ahead of myself, is 6, it's not 8, so it's not along there. So we'll highlight this part, that's where the green route carries on. Let's do the blue route down here. So 20 minus 6 is 14, so not here. 20 minus 12 is 8, so along here. Right, so we'll just highlight that. We'll go back to the green route and we'll carry this on here. So 15 minus 7 is 8. Yep, so we can go along there. 15 minus 18, well, it's negative 3, so this is not part of the green route. So we'll highlight the green route there. And we might as well finish it off. We can see that 8 minus 8 is 0. So this is where the green route finishes. So it sort of goes through here like this, through these vertices. And then we'll just finish this off. Well, 8 minus 8 is obviously 0. So this is going to be the last part of the blue route. So it goes through these vertices, and both of those have the same weight. So actually we have two routes. So I'll write the shortest routes are, the green one is A, B, D, E, H, and the other shortest route is the blue one, A, C, F, H, which both have weight 29, both have weight, or a weight, or distance, or time of 29. Now for part B, it asks us to find the shortest route from A to G. Now we don't need to work for anything again. We can just use our diagram, because the shortest route is already written down, and that's going to be 24. Yeah, whenever we do this algorithm, we're actually finding our final value is the shortest route to a particular vertex. So the shortest route to B is 8, the shortest route to D is 15, shortest route to F is 20, shortest route to E is 21. So the shortest route to G is going to be 24. So we're just going to work backwards on this one. So 24 minus 9 is 15. So we go along here. 15 minus 7 is 8. So it looks like we go along here. 15 minus 18 is negative 3. So it's not along there. And then 8 minus 8 is 0, so we go along here. So the shortest route from A to G, the shortest route is A, B, D, G, and has weight of 24. Okay, so this network below, this one, represents the road system in the city. Some roads are one way, as indicating by the arrow showing you can only go in that direction. The number of on each arc represents the time in minutes to travel along that arc. Show that there are two quickest routes, so we should get two routes in our answer from A to I. So that means my start is here and my finish is here. Explain how you found your routes from your labelled diagram. Right, so whenever we've got any directed arcs, directed edges like this, it means we can only go that way. So for example, from A I can go to B, I can go to C, but I can't go to E. I can go from E to A, or if, for example, I was at E, I could go to A, not to C, not to D, but I can go to F. No arrow means you can go either way. Right, so we start by saying A is the first one that we labelled, and it has a permanent value, final value of 0. Where can we get to directly from A? Well, B or C, not E because of the directed arc. So B will have a working value of 5, C will have a working value of 2, which has the smallest working value, C, so that now becomes its permanent value, and it's the second one that I've labelled. Now I look at where I can get to from C. Now I could go to B, not to A, E, or D. So let's write down these working values. So B will have a working value of 4, D will have a working value of 5, and then E will have a working value of 7. Right, which one of my vertices has the smallest working value? That is B. So that 4 becomes its permanent final value, and this is the third vertex that I've labelled. Right, which vertices can I get to? So D only, because this has already got a permanent value in it, so we don't go along there. So we go to D. That will give us another working value of 4 plus 4, which is 8. Okay, so now we look at what our smallest working values are from these two, and it's going to be 5. Now can you see the 5 is already put in there for us? Sometimes you have values that are put in already, so I'll put that in. And then what we're going to put in here is that this is the fourth vertex that we've labelled. Right, now we're going to put in where we can reach directly from here. So that is either going to be E, F, or G. None of those are directed. So since it's got a final value of 5, 5 plus 1, this will give this a working value of 6. This will get 5 plus 9, which is 14. And then here 5 plus 11 will give us 16. Right, which of these working values is the smallest? Well, it's this one here, E, which is 6. This will be the fifth vertex that I've labelled. So now where can I get to directly from E? Well, that will be one of these two, like this. So we will have 6 plus 8, which is 14. I'll put that down. So it's the same working value as the other root. And then here I'll have 6 plus 14, so I'll have a final value here of 20. Right, which one of those three has the lowest working value? Well, it's going to be F, 14. And this is now the sixth vertex that I've labelled. Where can I get to from F? So here, here, or here. So I've got 3 choices. So going to G, 14 plus 1 gives me 15. 14 plus 5 to H gives me 19. And 14 plus 7 to the finish gives me 21. Go around the algorithm again. Which one of these has the lowest working value? Well, that's G, and that's 15. So 15 now becomes the permanent value, and this is the seventh vertex that I've labelled. Where can I get to from G? Well, just to H, that's the only choice. So that means H is going to have a working value now of 17, 15 plus 2. Right, which of these has the lowest working value? That's H, 17. That is now the 8th vertex that I've labelled. And then, well, there's only one choice, and that's to go to the finish. And then that'll be 17 plus 2. So I get a working value of 19. I'll have 19 as the lowest value, working value, and that will be the 9th vertex that I label. Right, so now let's work backwards to find the shortest route. So the first thing I'm going to do is to write down the calculations. 19 minus 2 is 17. Okay, so we go along here. 19 minus 14 is 5, so we don't go along here. And 19 minus 14 is 5 as well. Not sure why I put 9 minus 14. That should be 19 minus 7, shouldn't it? That's 2. So we still don't go along that one, and we don't go along this one. Now, one thing we need to be careful of when we want to work out what the shortest route is, when we work backwards, we can go backwards along these arrows. It's a bit like retracing our steps. But what we can't do is we can't go forward. So I can't go this way when working backwards, because that's basically like saying, well, if I go forwards, I can go this way. You can't. So just take care of that. When you've got a directed network here, you can go backwards along along the arrows, but not forwards. So that means we can go backwards from H to G. So 17 minus 2 is 15, so that's fine. 17 minus 5, okay, well, that's not 14, so we don't go that way. So the next part of our route is going to be to here. So I'll just sort of colour those in so we can sort of see the route. Then from the 15 here, G, we can go 15 minus 11 is 4, so it's not this route because that's not 4 there, it's 5. And we can go, since we're working backwards, we can go backwards along the arrow and get 15 minus 1, which is 14. So this is the next part of our route, like this. We'll carry on going. I'll just do the calculation. So 14 minus 9 is 5. 14 minus 8 is 6. So I can go either way. So let me do that. And let's do this in a different colour here. So the last route is going to be the same for both, but the first part of the route is going to be different. Right, got to here. 5 minus 3 is 2. 5 minus 4 is not 4, so we don't go along there. And then from here, 2 minus 2 is 0, so we don't go along here. 2 minus 2, going backwards along the arrow, is 0, so that works, we can go that way. Now, from here, we cannot go this way. And we can't go forwards along arrows, we go backwards. So I'll have 6 minus 5, which is 1, so it's not there. But 6 minus 1 is 5, so we'll go up here. And then the rest is going to be the same, isn't it? 5 minus 3 is 2. So we go there and we go there, they're both going to be the same. So for part A, we've got 2 routes. So the routes are, they both start at A. And then the red one goes A, C, D, F, G, H, I, F, G, H, I. And then the other route also starts the same, A, C, D, but then goes E, F, G, H, I, G, H, and I. And both of these have weights of 19. Now, since this question says, explain how you found your routes from your labelled diagram, just writing this alone isn't enough. We need to have these calculations. So either have those calculations listed or on your diagram. So I'm just going to put in the final calculations that we sort of did manually. So I've highlighted them as well, just in case you want to have them listed. Now in part B, it says that road HI is closed due to roadworks. Find the quickest route from A to I, avoiding HI. Okay, now for part B, we don't have to do the whole question again. I've just taken out the calculations and just left the working on the diagram. Now, they said that this road is closed, so we can't go that way. So there's no point going to H to get to the finish, which is the route we took before. So I'm going to have to go from F to I, or from E to I. Now let me just take out this value of 19, because that was a working value that came from H. Okay, so I'll just take that out. Now what working values will I have? Well, 6 plus the 4, 14, which is 20, the 14 plus the 7, which is the 21. So with that working value of 19 gone, the smallest working value is going to be 20. So for part B, the quickest route from A to I is going to be slightly different. So we will have 20 minus 14, which is 6, 20 minus 7, which is 13. Okay, so it's not this route, it's this route here. Then we'll have 6 minus 8, which is obviously negative 2, so it's not this route. I think it was this way before, wasn't it? 6 minus 1, which is 5. So we go along here. Remember, you go backwards along arrows when working backwards. And then from memory, I think it was 5 minus 3, which is 2 minus, okay, 2 minus 2, which is 0. So this time maybe I will write my working down and show you how we'd probably write the solution if we were writing our working as a list rather than on the diagram. So I just need to show my backwards working, which was 20 minus 14 equals 6. So we know that that takes us from I back to E. Then after that we had 6 minus 1, which is 5, which we know takes us from E back to D. And then 5 minus 3 is 2, so that's D to C. And then C back to A was the 2 minus 2, which is 0. So C back to A. So that would mean A to C, C to D, D to E, E to I. And that has a weight, and it's to do with time, isn't it? So weight, or the time, would be 20 minutes now. So 1 minute longer because that road is closed. So you should now be able to do exercise 3D on pages 71 to 73. Just a quick recap of the algorithm, which is here, which is always also on the first slide, and also the way that we label our vertices. Just one note here, if we've got a directed network, that means we've got arrows along the lines. You can only go forward along an arrow that's facing that way. And then when we want to work out the actual route, once we've got to the end and we need to work backwards, we can only go backwards along like an arrow in the reverse direction.